Welcome to this tutorial on how to model a deep excavation in the finite element software ZSoil. The problem that was chosen for this tutorial is taken from a benchmarking exercise on numerical modeling in geotechnics. The original can be found under Schweiger 2002. You are looking at the original sketch of the problem. It consists of a deep excavation in Berlin sand. The excavation is carried out in 4 stages and is supported by a diaphragm wall and 3 rows of pre-stressed anchors. The problem is analyzed in plane strain conditions, and symmetry is taken into account. The groundwater table is set at 3 meters below the surface. During construction, it is lowered to -17.9 meters inside the excavation pit. In the depth of the base of the diaphragm wall, there is a hydraulic barrier, which should not be considered as a structural support, but having the same mechanical properties as the surrounding soil. We will model the soil with 2 homogeneous sand layers: medium dense sand above -20 meters and dense sand below. So let us now create our FE model. For that, open ZSoil. I'm using ZSoil version 24.08 from 2024, so if anything looks slightly different than on the video, it might be because you're using a different version. The first step is always to set the pre-selections for the project. Go to Control, Project Pre-selection. Version type corresponds to all the options that are available in the menus that you will be using during the model creation. For this tutorial, the basic version type is enough. The default analysis type is already correct as well in our case, as we will be solving a plane strain problem. Our problem type is not only deformation, but deformation and flow, as we will have a 2-phase model with soil and groundwater. Here, you can give your project a title and set the author and company name. Down here, you can define the unit system in which you'll later need to define your model parameters. Normally, you can leave it as is. You can display them here. So, forces will be in kilonewtons, etc. This message is just a reminder that whenever you make changes in the pre-selections, to please check that your drivers are still correct. I will explain later what drivers are. For now, you can just confirm with OK. Always also make sure to save your project. Go to File, Save, and save it somewhere on your machine. I've already done so, and we'll skip that. Next, we will draw the geometry of our model. To do that, go to Assembly, Preprocessing, and the preprocessor window will open. Here, you have all the tools to draw the geometry of your model. You can see here a set of predefined construction axes. We will define new ones in a moment. You may also be able to recognize these points here. They're called grid points. You can snap to them when drawing lines and points and other objects, but we will not use them in this tutorial. So, by pressing G, you can disable the grid points. So now, as I said, we will define new construction axes. In this Draw toolbar up here, you find the construction axes. One can define them arbitrarily. I'm just going to delete the ones that we don't need before defining the new ones. So first I'll define the vertical construction axes, specified here with X coordinates. By the way, you can see the coordinate system up here. So X is the horizontal coordinate and Y is the vertical coordinate. X is positive to the right and Y is positive in upwards direction. So, we will now define construction axes at X equals 0, 30, 70, and 110 meters. Then we go over to the construction axes in Y direction. And again, I will delete the default ones. And we define new ones starting at Y coordinate of -80, -40, -32, -30, -20, -16.8, -14.35, minus 9.3, minus 4.8, and 0 meters. Then you confirm with OK. Finally, you can see our newly defined construction axes. They will now help us to define the geometry of our model. Now, in the Draw toolbar up here, you find, for example, a rectangle, to be defined by 2 points. With that, we will now define the outer boundaries of our model, from the top left to the bottom right. And then, we will continue drawing with lines. By default, the lines would continue with every new click. So you would be drawing polygons. Because we want to draw single lines, we have to uncheck this Continue box here. First of all, we will draw a horizontal line over the whole model width at a depth of 40 meters. So here you have to check the Run Intersection automatically and do not show this query again checkbox. This will turn on creation of points wherever 2 lines that you draw intersect, which is what we want. So we confirm with yes. Then we draw another horizontal line over the whole model width at a depth of minus 20 meters. Then a vertical line over the whole height at 70. And at 30 meters, we draw a vertical line only down to a depth of 40 meters. And then some shorter horizontal lines that we will use for the excavation stages. So here at a depth of minus 4.8, minus 9.3, minus 14.4, and minus 16.8 meters. Be sure to not choose these midpoints here, but really the snaps to the construction axis that we've just defined. So these ones are for the excavation stages, and the next 2 for the hydraulic barrier at the foot of the diaphragm wall. At a depth of 30 and 32 meters. That's it. So we close by clicking the Close button. Next, we want to assign properties to the geometry. For example, first of all, we want to create a continuum with inherent material properties of our sand. For that, in Macro Model, we can define subdomains, and we have to define one for every one of these single rectangular subareas. We do that by selecting 2D continuum inside contour and click in each rectangle. You can see that by doing so, the color changes to salmon. Now, by default, subdomains have material number 1 assigned to it. You may recall that we want 2 layers with 2 different material definitions, medium dense sand above and dense sand below minus 20 meters. So what we're going to do now is select all the subdomains below these minus 20 meters and assign material number 2 to them. We can do that as follows. Still in Macro Model, Subdomain, go to Select in Zoom box. And then from the left to the right, select all of the subdomains below minus 20 meters. Now that we have selected them, we can select Update Parameters and update the parameters for all of the single subdomains at once. So we confirm with yes. Everything that we leave unchecked here will be left the same as it was previously defined. And we only really want to change the material number for the initial material. So we check this and specify material number 2 here, and then click OK. We will define the materials later on. Now you can click on Unselect All. And what you should see now is 2 different colors for the 2 kinds of subdomains. The ones to which we've just assigned material number 2 are depicted in a darker color. Over here, you can change to different tools for changing your view. For example, if you want to move around your canvas, you can select this hand here. If you want to select things, you can go back to the Standard Selection tool. Now we know that at the beginning, every one of these subdomains is present. But then, as time progresses, the staged excavation is to take place. Therefore, we need to define the excavation of these 4 subdomains here at certain points in time. So let's do that right now. So go to Macro Model, Subdomain, Update, Parameters. Then you can select each of the 4 subdomains after the other and define its removal at a certain point in time. The way to define this is by specifying an existence function. Existence functions, like their name already suggests, are used for specifying the existence times of continuum subdomains or structural elements like beams or trusses. An element may, for example, exist up to time t1 and then be removed from the model. And maybe later on at t2 it will even reappear into the model. Existence functions, just like materials, are also labeled by a numbering system. We will define the first excavation stage with existence function number 1. Then, it is wise to additionally also define a load function for excavated soil. Existence functions themselves are step functions, meaning that the elements are removed entirely at once. First of all, this is not really realistic, and secondly, it may lead to convergence problems for large excavation stages. Load functions, or more fittingly, unloading functions, offer the possibility for a gradual excavation process. They are also labeled by numbers. We can always use the same load function for all excavation stages, namely load function number 1. We will define it later. So then click OK. And as I said, click on the second excavated material. Specify existence function 2 and load function 1. And for the third excavation stage, existence function 3 and load function 1. And for the fourth excavation stage, existence function 4 and load function 1. Now visually, you cannot really see that you've changed anything at the moment. This is because the display color for the subdomains is set by initial material at the moment. You can change the display color to existence function, and then the colors change. Gray areas don't have any existence function assigned. Our 4 excavation stages all have a unique color because they are defined with different existence functions. Next, we're going to define a finite element mesh for all the continuum subdomains. For this, still in macro model, subdomain, you have this option here. Create virtual mesh. This creates only a virtual mesh. No actual finite elements will be created. Only after we've created the virtual mesh for all the subdomains will we turn it into a real mesh of finite elements. So click here on Create Virtual Mesh, and we will start over here with the first excavated part. You can click inside the subdomain, and this window will show up. There are different methods for meshing: the structured, the unstructured, and the through morphing. For now, I'm only going to go into the structured method because we have perfectly rectangular subdomains, and the structured mesh will function perfectly. The way the mesh is defined is by a split on 2 edges, which defines the number of elements along them. The edges are defined by 4 numbered corner points. You can see them here at the moment: 1, 2, 3, and 4. If for some reason the numbers are not assigned automatically or you need to change them, you can reset the control points here by picking them manually. So for this first subdomain, we want 12 elements horizontally and 6 elements vertically. By looking at the control point numbering, we therefore know that the split for edge 1, 2 should be 12, and for edge 1, 4 it should be 6. This checkbox down here, Adjust Split to Existing Meshed Subdomains, is very convenient, and we will leave it checked. For the virtual mesh definition of the first subdomain, it does not really do anything. But for the subsequently meshed subdomains, it makes sure to make your mesh definition compliant with already existing mesh definitions in neighboring subdomains. So leave this checked and click on Create Virtual Mesh. Now you can see the mesh that we've just created. If you need to zoom in or move around at any point in time, as I've said, you have this hand here for moving your canvas around. With the mouse wheel, you can zoom, and this will always be centered. So this hand tool is very convenient to use when wanting to zoom. So now we continue with the next subdomain. Click again on Create Virtual Mesh, and then inside the second subdomain. We want to have the same split for this subdomain. So horizontally, 12 elements, and vertically 6 elements. Again, click on Create Virtual Mesh. Create the virtual mesh for all of the remaining subdomains as shown here in this picture. I'm just going to quickly do that now. When you're done, the final mesh should look like this. By the way, when you're somewhere zoomed in or zoomed out, you can press Ctrl F, which brings the whole model into view again. So just close the meshing window for now. Now we will move on to defining the retaining wall. We will model it not as a continuum, but as a structural component, so a beam. To create such a beam, go to Macro Model, Subdomain, and there you will find Beam on Objects. But we first need to select the lines on which we want to create a beam. You can do this here in the Global Selection tools. Use this Select Elements in Zoom Box tool, and then from top left to bottom right, select these 7 lines going down to -32 meters. Then click on Beam on Objects. Yes. Select Initial Material as 3, as we will later define Material 3 for our wall. Set Existence function to number 5. We've already used the first 4 for the excavation stages. We do this because the diaphragm wall will be constructed only at a certain point in time throughout our modeling sequence. Then click OK. Next, we need to define a virtual mesh for the just created beam. At the moment, we still have the lines selected on which we define the beams, but not the beams themselves. So click on Unselect All, and then again in the Global Selection tools on Select Elements in Zoom Box. Reselect these 7 lines, including now the beam objects. Then still in Macro Model, Subdomain, click on Create Virtual Mesh. Yes. And now you would technically have to define the split. But as before, if this Adjust Split to Existing Meshed Subdomains box is checked, it will create a mesh matching the one from adjacent continuum subdomains that are already meshed. And this is what we want. So we confirm by clicking OK. Now you can see the just created nodes here. Now what else do we need? We need to define an interface on the beam acting between the beam and the surrounding soil. For that, under Macro Model, click on Interface and then on Structural Subdomains. Confirm with Yes. We now have to define the 2 interfaces on the one side and on the other side of the beam. The 2 sides are denoted positive and negative, depending on the beam's local coordinate system. We want identical interfaces on both sides. The material that we are going to define for the interfaces will be number 7. So set material number to 7 for the interface on the positive side and also for the interface on the negative side. Also on both sides, set the existence function to number 5. This is the same one as we've set for the beams. And then on both sides, click on Modify. Our settings or our changes will then be updated and displayed down here. Then confirm by clicking OK. And now you see these purple lines here representing our interface along the beam sections. Click on Unselect All. Next, we're going to define the groundwater table. Press Ctrl F to see the whole model again. Then go to the Edges and Faces Selection toolbar. In contrast to the Global Selection tools, this allows you to only select element faces and not geometric lines. We choose Select Edges in Zoom Box and select all the edges of the right boundary. We want to define the groundwater table with a pressure boundary condition. To do that, click on Macro Model, Pressure Boundary Condition, and then Fluid Head on selected edges. We're going to define the water pressure with a head of -3 meters. What it does is create a boundary condition for the water phase, as well as one for the solid continuum phase, which is the soil. But we can actually disable the creation of the solid BC for this case, because we will horizontally fix all the nodes at the side boundary shortly anyways. So you can uncheck this Create Load box here, and then confirm with OK. So we've now defined the pressure boundary condition on these edges. But there's something more we need to do. The thing is that these edges can either be underwater or above, but this is neither clear a priori, nor does it have to stay the same for the whole calculation. There are specific elements available called seepage elements, which handle this possible change in behavior when wet changes to dry or vice versa. So in Macro Model, click on Seepage, on Subdomain Edges, and confirm with Yes. Choose Material Number 8, which will become our seepage material. Then confirm with OK. So we see these blue lines here, which tells us that we have defined seepage elements on these edges. Now click on Unselect All. What we need to do next for the water boundary conditions is also define them for this boundary here, the symmetry boundary of the excavation pit, because we will lower the groundwater before the excavation stages. So again, in the Edges and Faces selection tools, choose this one here and select these 5 edges here. For these, we will also define a pressure boundary condition and seepage elements. So as before, in Macro Model, create a pressure boundary condition with a fluid head. We want to define a fluid head changing with time, simulating the lowering of the groundwater table. We can do this with a load function and specify load function number 2. We set the fluid head to 1 meter and will specify the actual value later on in the load function. We can also uncheck this Create Load tick box here for the same reason as at the right model boundary. Then we confirm by clicking OK. Also, again, we need to define seepage elements on these edges because the water table is going to change with time. So again, in Macro Model, choose Seepage on Subdomain Edges. And again, use material number 8, our seepage material. Leave existence function as 0 for now. We're going to specify those for the individual boundaries of every excavation stage separately in just a second. Click on Unselect All. Go again to Macro Model, Seepage, if you're not still there, and click on Update Parameters. And then on the first edge here, specify existence function number 1, also corresponding to excavation stage 1. Click next to the line of the second excavation stage. Set existence function to 2. The third one gets existence function 3. And the fourth one existence function number 4. We're now ready to turn our macro model into a finite element model. And what this is going to do is create the finite elements according to our chosen virtual mesh and transfer all the information we have given to our macro model to the finite elements. We do this as follows. First of all, click Ctrl F to see the whole model again. Then click on Unselect All. Then select everything with Ctrl A. Finally, under Macro Model, Subdomain, Mesh, we click on Virtual to Real Mesh. Confirm with Yes. Now you can see that actual elements with nodes have been created according to our virtual mesh. Click Unselect All. The next step for us is to define the pre-stressed anchors. The starting points of the anchors should be connected to our beam or our retaining wall. Now the beam does not necessarily have nodes right at the future starting points of the anchors. This is not a problem, but it means that we have to define these geometric points first, then create the anchors, and then connect them to the beam. On a side note, another way to define the anchors and connect them to the beam would be to manually find the beam nodes closest to the 3 anchor starting points and move them to the correct position. The subsequently defined anchors would then automatically be connected to these beam nodes. In this tutorial, we will nevertheless apply the first method. So for that, I'm going to turn off the visibility of some of the objects in our model. There is this visibility window here where we can, for example, turn off all the macro objects and the FE objects, and this leaves us just with the geometry. Then we're going to create points by clicking on Point in the Draw toolbar. The way the points are to be defined is by 3 coordinates, x, y, and z, separated by a blank space. The coordinate of the first anchor starting point is 30, minus 4.3, 0. You can see that a point has appeared here. The starting point of the second anchor row is 30, minus 8.8, 0. Confirm by clicking Enter. A second point has appeared. Finally, the starting point of the third anchor row is 30, minus 13.85, 0. Click on Apply and the third point appears. We can close this window and now have our 3 points, which will serve as starting points of our anchor rows. You can define anchors either in the macro model or in the FE model. I'm going to define them in the FE model, as this offers the possibility of defining them by specifying a starting point, a direction vector, and their length, which I find the most convenient. So click here on FE model, anchor/truss, and choose point plus vector plus length. Click on the first point that we have defined, and then we need to set the direction vector of the anchor row, which in our case is 0.89 and minus 0.45. Then we need to define its length. It is 11.8 meters long. Here you see the choice for the anchor starting and end nodes to be linked to other elements or nodes in the model. Node 1, which is the starting node of our anchor, should indeed be linked with the adjacent structural element, the beam. The settings for node 2 are also correct. The end node of our anchor should not be linked to anything because we're going to have a fixed anchor zone, which gradually transfers the forces into the surrounding soil. Set the material for the first anchor row to number 6 and the existence function also to 6. Then we move on to the definition of the fixed anchor zone. We do want a fixed anchor zone, and we want its length to be 8 meters. Set the material for the interface of the fixed anchor zone to number 5. We want to define the mesh split by a number of segments which we choose to be 5. This then leaves us with defining the pre-stress. We do want a pre-stress, and we want to define it by force. And this force should be 768 kilonewtons. This pre-stress force will not always be present, so we specify existence function number 7. Then you can confirm by clicking OK. Now you can see the first anchor row. For the remaining 2, we're just going to continue similarly. So we're still in the point vector length definition mode, and can click on the starting point of the next anchor row. The direction vector is the same, so 0.89 and minus 0.45. The length is 15.8 meters. We also want to link node 1 with the beam. The initial material is 6 again, and its existence function is 8. Then the fixed anchor zone should have a length of 8 meters. Interface material number 5. The number of segments again, 5. The pre-stress, again by force, should be 945 kilonewtons. Its existence function is number 9. Click on OK and define the third anchor row next. Again the same vector, 0.89 minus 0.45. The anchor length this time is 15.3 meters. Link node 1 with the structural element. The initial material is 6, which is the same as for anchor row 2. The existence function this time is 10. The fixed anchor zone should again have a length of 8 meters. Interface material number 5. 5 segments. The pre-stress is defined by a force of 980 kilonewtons, with existence function number 11. Click on OK. We have now defined our 3 anchor rows. We can turn back on the visibility of the FE and the macro objects. This is best done by pressing the Reset All button here. If you zoom in on the starting point of one of the anchors, this green bit here indicates that the starting node is linked to the adjacent beam element. The next thing we will define is the hydraulic barrier. We want to have a layer here which acts as a hydraulic barrier. In this example, we will achieve this by setting a very low permeability for these elements at a certain point in time. So we're going to switch the material for this element row to material number 9, which will be identical to the material of the surrounding soil except for a drastic reduction of permeability at a certain point in time. I'm going to again turn off the visibility of the macro model, and this time also suppress the geometry. Just to make sure nothing is still selected, click on Unselect All. Then from the Global Selection tools, use Elements in Zoom Box. We will now select these elements here from left to right. And then in FE Model, Continuum 2D, Update, and Parameters, we can update the parameters just for these elements. We want to change the initial material from number 2 to number 9. Confirm with OK. Click on Unselect All and zoom out with Ctrl F. And now the last thing we still need to do in the pre-processing module is to create the continuum boundary conditions. So in FE Model, we go to Boundary Conditions and select Solid BC. With such regular model boundaries as in our example, we can create the boundary conditions very conveniently with this OnBox command here, which, as you can see, creates boundary conditions along the side and the bottom model boundaries. These are symmetry boundary conditions on the left and the right side, and full fixities at the bottom. You can check the little red lines. They correspond to the direction of the fixed displacement degree of freedom. Here for the bottom nodes, you can see 2 such lines, one in each coordinate direction, and for the side boundary nodes, only 1 red line in X direction. Now we've finished our definitions in the pre-processing module. So we can go to File, Save Model and return to Main menu, and confirm with Yes. What it does now is perform a data verification check. And indeed, a warning is issued, which says that there are some singular nodes at the end of structural elements. In our case, this means that the node at the toe of the wall beam is separated from the underlying continuum node due to the present interface along the beam. This can easily be fixed by linking the structural node to the continuum. So click Return to the application and go to FE Model, Interface. Select Singular Interface Nodes. The singular node is now selected and highlighted in red. Then click on Link Interface Nodes and confirm with Yes. Now try to exit again. And indeed, the data verification does not result in any errors anymore. In the next step, we're going to define our materials. Under Assembly, Materials, you find all the material definitions of your model. And as you can see, 9 materials have already been created automatically during our pre-processing actions, assuming default material parameters. So it is now our task to adjust these material definitions to our preferences. During pre-processing, we've referred to the different materials with these unique numeric identifiers here. Depending on the type of object we've assigned the materials to, the material types were chosen. We've got, for example, 3 continuum materials for our different soils, a beam material for the diaphragm wall, a fixed anchor zone material, 2 truss materials for our anchors, a material for the contact between wall and soil, and a seepage material. So first, let us define our soil materials. Number 1 corresponds to the medium dense sand. Click on the material and then on Modify. Name it medium sand and change the material formulation to HS small strain stiffness. This is the well-known hardening soil model with option for an increased small strain stiffness. In this tutorial, I will not go into the details of this material model. You can, however, find all the necessary information about it in the ZSoil documentation under Reports. Hardening Soil Small Model. With Material 1 still selected, on the right side here, you now have different categories of material parameters. Some have to be checked, while others are optional. You could, for example, uncheck Flow to make a material impermeable. We additionally check Initial K-Naught State, which enables us to define the initial stress state directly by specifying K-Naught values. You can now enter all the parameters of the 5 checked categories as shown in this picture. We then continue with material number 2, our dense sand. Again, click on the material, then on Modify, and name it dense sand. Change the material formulation to HS small strain stiffness, and confirm with OK. Make sure to again check Initial K-Naught State, and then enter all the parameters of the 5 checked categories as shown in this picture. Next up is the material for the diaphragm wall. Click on material number 3, then on Modify. Name it Wall, and confirm with OK. The wall is made of concrete. Therefore, in the elastic parameters category, set Young's modulus E to 30 gigapascals and Poisson's ratio nu to 0.2. Concerning the unit weight, we want to consider that the beam in our model has 0 thickness. Therefore, there are soil continuum elements even in the space where technically the wall would be. For that reason, we set the unit weight of our beam only to the concrete weight minus the weight of the soil so we don't end up with too much mass in our model. That is then roughly 25 minus 20 equals 5 kilonewtons per cubic meter. In the cross-section category, we enter a wall thickness h of 0.8 meters and set the width b to 1 meter as we have plane strain conditions. The rest you can leave as is. Next, we will specify the parameters for our 2 anchor materials. We need 2 separate materials because the anchor spacing in the first anchor row is 2.3 meters, and in rows 2 and 3 it is 1.35 meters. So name material 4, anchor row 1, and material 6, anchor rows 1, 2. Then set Young's modulus E to 210 gigapascals for both materials. The cross-sectional area is 0.0015 square meters for both materials as well. And as I've said, the spacing of anchor row 1 is 2.3 meters, and for rows 2 and 3 it is 1.35 meters. For material number 5, we leave the default parameters and just change its name to Fixed Anchor Zone Interface. Material number 7 defines the contact law in the wall-soil interface. Rename it to wall-soil contact. We can uncheck the flow checkbox because a diaphragm wall can be considered an impermeable barrier. In the nonlinear checkbox, we can specify the strength parameters of the contact law. We choose a slightly reduced friction angle of 28 degrees and leave the cohesion at 0. Finally, we are going to set the elastic normal stiffness of the contact. We choose the Kn multiplier slightly higher than the default value and set it to 0.05 in order to limit contact penetration. In reality, contact penetration does not exist, and it is only a numerical construct introduced to be able to deal with contacts. So setting the Kn multiplier too high may result in convergence issues. It is therefore advisable to start with lower values and work your way up in subsequent calculations, until you see that, for example, the bending moments in the wall are not affected by the contact stiffness changes anymore. Material number 8, corresponding to the seepage elements, we are going to leave with its default parameters. Just rename it to seepage. Finally, that leaves us with material number 9, which we have foreseen for the dense sand that turns into the impermeable barrier at the foot of the wall underneath the excavation pit. We can therefore first copy the parameters of material 2 and then do the remaining modifications. So select material 2 and click on Add Selected Material to Database. Create a new database and confirm with OK. Then click on Material 9, Modify, and Take Material from Database. Select the database that you've just created. Choose the last material added. Click on Take Selected Material. Rename it to Dense Sand Barrier. And then confirm with OK. Material 9 now has the same properties as Material 2. Now we just need to define a reduction of permeability at a certain point in time. The permeability coefficient K is defined in the flow category. We're going to leave the K value of 5.62 specified here, as it initially has the same permeability as the sand of Material 2. We can then specify the permeability reduction with a load function on K. To do that, switch the data mode to load function and set the load function for K to number 3. We will define the values of the load function at a later stage. We now have specified all the necessary material parameters and can exit the materials window. Finally, this leaves us with defining the analysis sequence, including the various existence and load functions. First, enter the driver's definition menu by clicking Control, Drivers. The analysis starts with an initial state driver, imposing the initial stress state according to the K0 value we have specified in the materials, with 0 deformations. The initial state for the pore fluid pressure is also calculated. You can leave the default settings for the initial and final load factors and the increment. After the initial state driver, we define a time-dependent driver of type driven load plus steady state flow, with starting time 0 and end time 7 in increments of 1. Time, in this case, is just a fictitious quantity, as the chosen driver calculates a steady state of pore pressures in each increment, and no other time-dependent quantities are present. We can confirm our choices with OK. Now it is time to define the staged excavation process, including dewatering. We will define it according to this table. The dewatering happens between t equals 0 to 2, with construction of the diaphragm wall at t equals 1. Between t equals 2 and 3, the hydraulic barrier will be activated. Then follow the 4 excavation stages from t equals 3 to 7, each within a time span of 1. The anchors will be set and pre-stressed at the end of the respective excavation stages. In ZSoil, the desired model sequence in this table can be defined with the use of existence and load functions. Let us start with the existence functions. For that, go to Assembly, Existence Functions. As their name suggests, existence functions define at what times elements exist and at what times they don't. So according to our model sequence table, we define the following existence functions. Excavation 1 from 0 to 3. Excavation 2 from 0 to 4. Excavation 3 from 0 to 5. And excavation 4 from 0 to 6. The specified existence times are sharp boundaries. So by our definition, purely with existence functions, the entire material of an excavation stage would be excavated in one glimpse. This is not realistic and can also lead to convergence problems. We can solve this with the help of a load function defined on the elements themselves, starting at the time of the element deactivation and decreasing gradually from a value of 1 to 0, over, for example, a time span of 1. During the pre-processing, we've already assigned this kind of load function to the elements that are to be excavated, and we will define the load function once we're done with all existence functions. The next existence function is for the diaphragm wall, which should exist from time 1 to the end. Then come the anchors. We choose to set each anchor row at 0.01 before the end of the respective excavation stage. Each pre-stress force of the anchors is set to be active at the appearance of the anchor and for a time span of 0.01 only. In this way, the anchor is inserted into the model already carrying the internal pre-stress force while being in equilibrium. When the internally applied pre-stress force is then turned off by existence function, the force is transmitted to the surrounding soil in search of a new equilibrium. So that's it for the existence functions, and we move on to the load functions. Go to Assembly, Load Functions. In our example, we need 3 load functions. The first one is the one previously mentioned taking care of the gradual unloading rate during element removal. Set the name to Unloading and click on Modify. Set values of 1, 0.5, and 0. At times, 0, 0.5, and 1. The point at 0.5 is not strictly necessary, but will lead to a forced calculation step in the analysis, no matter the time step definitions in the driver. For this load function, it is important to set shift origin to element deactivation time. This enables the use of a single load function for every excavation stage, as the specified times are then relative to the element deactivation time. Next, choose Load Function 2 and name it Dewatering. It is the one controlling the pressure head boundary condition on the left side of the model. Click on Modify and then set values, -3 and -17.9, at times, 0 and 2. The values directly correspond to the fluid head, as we have defined the pressure head with a value of 1 in our model. Finally, choose Load Function 3, name it Impermeable Barrier, and click on Modify. This one is associated with the permeability of material 9, becoming the hydraulic barrier. Set the values to 1 and 10 to the -6, at times, 2, and 3. Exit with OK. We are now done with all the definitions of our model and are ready for calculation. To run the analysis, go to Analysis, Run Analysis. This window will open, displaying information about the current solver status. It is divided into different sections. Here it displays the driver that is currently running. At the moment, this is the time-dependent driven load plus steady-state flow. So we've already missed the initial state driver. Then there are two spots displaying the global analysis time that is currently being solved. The current iteration of this solver step is shown here. Up here, the currently used type of nonlinear solver is given. Then, this section over here contains information about the current convergence status. Convergence is evaluated for the solid and the fluid phase separately. The current values of different convergence norms are displayed here. You can find their definition in the ZSoil theoretical manual. The same values are given numerically also over here. The tolerances for the norms having to be met for convergence are displayed here. Finally, down here, you can stop the computation, view the log file, or enter the postprocessor at any time during calculation. The postprocessor will, of course, only contain the results that have already been calculated. Nevertheless, this can be useful for early detection of mistakes in your model. As soon as the calculation has finished, the window disappears. We can view the results under Results, Post-Processing. A post-processor window will open. What we see here first is just the input data, similar to what was displayed in the pre-processing module. To view actual results, we can go to this graph option toolbar up here and click on Results, which will show us options for different types of results to display. We can, for example, have a look at the deformed mesh. The Settings button here contains the settings corresponding to the selected results type. For the deformed mesh, the settings consist only of the deformation scale factor. By default, automatic scaling is active, with a factor of 208 in our current case. Let's change it to a factor of 100 and confirm with OK. You can immediately see the effect. A more convenient way to change the scale factor is on your keyboard with the page up and page down buttons. The currently displayed deformed mesh corresponds to the displacements at a global time of 7. Here we can see all the time steps that have been calculated, and we can select any one of them for the display of results. So for example, at the end of the second excavation stage, the displacements look like this. There's also a more convenient way to switch between time steps on your keyboard by using the plus and the minus buttons of the numeric keypad. To the left of the time step selection, you can set a reference time step. The displayed results then correspond only to the increment between the reference and the current time step. So if we, for example, set the reference time to 4, while keeping the current time at 5, what we see are the deformations occurring during the second excavation stage only. With the Page Up button, the scale can be altered for better visualization. Another way to look at the displacement results is by displacement vectors. Again, you can scale them with the Page Up and Page Down buttons. The vectors provide an overview of the general displacement field in a qualitative manner. To display results in a more quantitative manner, there is a results type called Maps, which provides contour plots of various quantities. Under Settings, we see that there are element quantities and nodal quantities. The first nodal quantity are the displacements, where the selection of a component x, y, or z, or the absolute value of the vector is also required. The bounds of the contours are automatically set to the occurring extreme values, but you can change them by entering specific values here. So this is the contour plot of the absolute values of displacements during the second excavation stage. Now, besides the displacements, the pore pressure is another important nodal quantity that can be displayed in a contour plot. There's no component to be selected. For the pore pressure, it is usually helpful to change the default bounds, because positive values of pore pressure are also displayed. In the calculation, this pore water suction has of course no impact because the saturation in the corresponding areas is also zero. For that reason, we set the minimum, for example, to minus 400 kilopascals, and more importantly, the maximum to 0 kilopascals. Change the reference time step back to not selected, and the current one to 0. The groundwater table can be identified where the pore pressure is 0. We will now follow the pore pressure evolution throughout the analysis with the plus key on the keyboard. At time 1, the dewatering is underway, and on the left side of the model, the water table has dropped. At time 2, it has dropped even more, and we also notice that the impermeable wall has been created. At time 3, the hydraulic barrier down at the foot of the wall has been activated, basically leading to two separate homogeneous pressure head fields, one inside the excavation pit and another one outside. From here on, pore pressure does not change anymore with further analysis progression. Qualitatively, the pore pressure results are exactly as expected. Another quantity to display are, for example, the stresses. They are an element quantity. Both total and effective stresses are available, with all the stress tensor components and some invariants. Component Y corresponds to the vertical normal stresses. You can check the definition of the coordinate system up here, with the x-axis in red and the y-axis in green. Then, down here is the real current coordinate system used in the model. The green arrow points upwards, making y the vertical coordinate. We start at the initial state and see the undisturbed vertical stress field as we would expect it. With increasing analysis time, the effective stress field changes, for example due to the dewatering. Finally, we are interested in the sectional quantities of the structural elements. For example, the beams or the trusses in our model, representing the diaphragm wall and the anchors. The corresponding results type is results in beams, trusses, piles, nails, anchor fixed zones. Let us select the final time step. In the settings, we see that currently the beam moment MZ is selected for display. For a correct interpretation, we need to know the local basis of the beam representing our diaphragm wall. This can be done in View Data. In the visibility section over here, we can suppress some objects that we do not need at the moment. Suppress everything but the beams. Then, here on the right, turn on Local Bases on Beam. The local basis of each beam element has appeared in view now. Zoom in more closely, which reveals that the red line points downwards and the green line points to the right. And if we look back up here, red means X, green means Y. We therefore know that the Z-axis points towards us. Now that we know the direction of the Z-axis, we can go back to the results in beams. So by having looked at the local beam bases, we have confirmed that the selected beam moments, MZ, are in fact the bending moments of interest to us in our plane strain calculation. A useful setting for structural forces are numeric labels for local maxima and minima. They can be turned on here. Also, at the right end of the window there is a legend, color mapping values to each of the colors used in the plot. Besides the bending moments in the beams, you might be interested in the normal forces in our anchors. So down here, select NX and uncheck MZ up here. By pressing page down, you can adjust the scale so that nothing overlaps. We can see that there is tension in the anchors and compression in the wall due to the anchors. Surely you have noticed that since we entered the structural results, only structural elements are being displayed. You can change this default view and turn back on, for example, the continuum elements. Furthermore, some nice settings could be to suppress the inter-element lines and turn on the domain edges and the colors for different materials. This provides a bit more context on where the structural elements are situated in the model. So this was a short introduction to the postprocessor of ZSoil, with a focus on some of its most important aspects. With that, I'm also at the end of this tutorial on how to model a deep excavation in ZSoil. Of course, there are many other aspects and functionalities of ZSoil that were not covered in this tutorial. I encourage you to have a go at ZSoil yourself, watch other tutorials, and read up on important topics in the collection of ZSoil manuals and the Getting Started with ZSoil textbook. Thank you for watching, and goodbye.